So, thank you for all being here. Good morning to everyone. I'm going to present this work we are working on. I'm a PhD student at UMass Lowell from Crisis to Opportunity, Enhancing Energy Resilience in U.S. School Buildings. Yeah. So weather-related power outages are rising. This is our motivation behind this work. No, this is NASA picture, no, in Puerto Rico. You can see here from August 2022 to September, several days have passed, and there are important regions that still doesn't have return power. So this problem is not only in the Puerto Rico, in these territories, but also in the main US. No, from 2000 to 2021, there is an increase in weather-related power outages, more than 80%. So other weather-related outages rose more than 70%. This past decade compared with the previous one. On the other hand, we have our school infrastructure is aging. 50 years is the average average age of school buildings in the United States, and this represents that these buildings are very energy inefficient, and there is a lot of money that is spent on energy bills that could be spent on books or computers for students. So the PV price has decreased dramatically in the last couple of decades. 26 cents per watt is the price of PV panels globally in 2022, but less than 6% of school buildings are using PV in their operations. So there is an opportunity to boost the schools' energy efficiency and resilience with PV. So, but there is no perfect solutions. There is only trade-offs. So our research is based on how these school buildings can be converted to energy resilient hubs, and how these retrofit strategies can vary in different climate zones, and how do these interventions impact buildings' resilience and sustainability, considering the effects of climate change in work forecasts. So our assessment takes 3 stages. Now we have a model that has 3 parts. The building model, we are considering historical and forecast weather data. Next, we are going to use a solar PV model, considering connectivity to the grid, the PV system, and the battery. And we are simulating normal operation and also power outages. And then we are considering the life cycle. So we are studying the whole food systems, from cradle to grave, with life cycle modeling, including several impact categories, not only global warming potential, but others as well. So we started our study focusing on the regions that has an increase in frequency in power outages related to weather. So there are 4 states. We are considering also Puerto Rico as a territory. And we are also mapping the different climate zones and moisture regimes. So based on that, we choose 8 locations for our study. Now, most of these locations are on the humid side, but we are considering a dry zone, 3B in El Paso, and San Francisco as a marine regime from moist. So for the building model, we are considering a primary school building constructed before 1980. These are the reference building benchmark from the Department of Energy. And for the simulations, we are using the glass. So this is our base case scenario for all the 8 locations we considered. if you can see here, there is lighting, it's an important demand, an important contribution for the demand. Cooling is important for warmer climates, heating is important for colder climates, but we are also comparing with the standard. So if you can see here that in all cases, the energy use intensity based measured in megajoules per square meter per year, is double the current standard. So there is a pressing need for retrofit these buildings. So this is the strategies we are considering. We are considering passive strategies in the roof, exterior walls and windows, cooling roof with coatings, also cooling walls in some zones, also with coatings, replacing windows, and we also considering active strategies, and lighting. For the HVAC system, for example, in heating, we are replacing natural gas heating system with electric heating system and increasing the efficiency of the equipment. So as an example, you can see here how these different strategies impact the total demand for the buildings in 1 year. And there is a difference between different climates. So you can see here this as well. Lighting and HVAC systems has the highest potential for reduction. Regarding passive measures, roof has a higher, less from the passive measures is that it has a more potential for reduction. Overall, there is an important reduction based on the base case with the retrofit building. It's more important in warmer climates than in colder climates. In warmer climates could be around 60%, in colder climates a little bit less, but this is a high potential for reduction. So how with different weather climates this impact is the energy demand. So in the left, you can see for a hot and humid climate as in Houston, there is an increase if we leave the building as it is, business as usual, there is an increase to 3% for the whole period in the energy demand. But with the retrofit building, there is also an increase because when we change the polar climates, but it's less than 1%. In comparison with a mixed and humid climate in North Carolina, there is a reduction less than 1% of energy demand because it's polar climate. But with the retrofit building, there is a potential for reduction around 3%. So for the solar model, we are considering, we are using the tool from Andrea, the system algorithm model tool, and these are our constraints. Sorry. No, these are our constraints. 80% of the roof area is available for PV installation. We are considering the local electric tariffs, maybe in a similar climate zone or similar potential for solar, similar resource. There is a difference in the results because of the electric tariff. The critical load factor for during an outage is 30% of the normal load factor. We simulated a single event outage for Puerto Rico and multiple event outages for other locations. And the duration of the outage, we chose the maximum KD reported. And what is KD is a metric, reliability metric related to how long takes to restore power after an event. So based on that, we simulate that and we optimize the system based on resilience. But also, we are considering the net present value. So at least the net present value has to be positive, to be like economically viable. We want to be these solutions be sustainable. So that's why we have a range between PV sizes, battery power, capacity, and also how much electricity we can offset with the PV instead of using or buying from the grid. Could be from 20 to 80%. So these are the locations we choose. For example, in San Juan, we can offset 80% of the electricity using PV. This is, I think, from all the locations we consider, this is the the size of the PV system and the battery is the largest from San Juan, but it's also related not only for the solar resource, but related also with the electric tariffs over there. No, it's a higher, electric tariffs are higher than in other places in the US, so it's economically more advantage. No. In other places, there is a range, not on the results, no, because of that, the economic viability and also the solar resource. But even in colder climates, it's possible, to have resilience. The second bar, in every chart is how much hours of resilience we can achieve with the system. And the third bar is the LCOE, for the whole system. The life cycle cost of energy. So for the environmental footprint, of our system, we did a comparative life cycle assessment. From the business as usual, no retrofits connected to the grid, and with the retrofit building, solar PV plus battery and connected to the grid as well. So the functional unit is 1 square meter of PV, floor area along the lifespan of the PV panel, at least 25 years. So these are the life cycle stages product system. We have from cradle to grave, production, construction, use, and end of life. And for this study, we are considering these life cycle models. We are for use, for example, we are considering energy use, water use. These are considering the environmental impacts, and the others are embodied impacts. Construction, manufacturing, and end of life are considered embodied impacts. So this is an example of our results. These are normalized results. So 1 or 100% is the base case, and the other one is compared to that. So for 5 environmental categories, including global warming, there is a reduction of 60%, on the total environmental impact for the whole period, that is 25 years. But for other environmental categories, for other environmental categories as ecotoxicity and territorial acidification, there is a reduction, but it's not as high as the other impact categories. And for mineral resources scarcity, there is also an increase. And H2, we are going to see in another slide regarding the manufacturing of the PV and the battery. So as we were talking before, second life batteries and these strategies of circularity will help to improve the environmental footprint of these type of designs. So this, for global warming, you can see here the contribution. So which stages contribute to this environmental impact? So for the base case scenario is the electricity from the grid, as the highest contribution. In the retrofit scenario, the electricity from the grid is a contribution, but it's also an important contribution, the retrofit measure. So improving the windows, improving insulation will have an impact on this category, but overall there is a reduction on the environmental impact, around 60% reduction. But the embodied impacts become important. And there is a similar thing for mineral scarcity, but we have that there is an increase, because of the use of PV and the batteries, there is an increase of this impact category. So we need to assess, maybe strategies with circularity to improve the environmental footprint of these solutions. So as a conclusion, energy resilience in school buildings can be achieved, improving retrofit with passive retrofit measures, and also with plus PV plus storage, even in colder climates, could be achieved. And our next steps in our research is conduct a sensitivity analysis with longer power outages, maybe days. It could be, for example, in Puerto Rico, that's happening. Extending also to different climate zones and locations, not only in these higher frequency power outages, and also analyze the implementation of circularity strategies to enhance the environmental footprint of the process. So thank you, and I will be open to answer your questions.
Thanks a lot for your very interesting presentation. I wanted to know about like number one, like how do you define resilience? Is it against certain particular hazard, or is it a generic resilience? And like if you could detail a bit on this resilience-based optimization, how does it work?
Yeah, well, I base this resilience is energy resilience, no? It's to withstand power outages. So the idea is when there is a power outage, school buildings, we chose school buildings because when there is a weather event and an emergency, school buildings are immediately like shelters for the community. So there is an important building for community. So well, that's we chose school buildings. And the idea is when there is a power outages, these school buildings can provide shelter and has environmental comfort for the people that is there. No, I think after one of the hurricanes in New Orleans, no, all the people were moved to a stadium and they have to move the next day because the temperatures inside the facility were so high that they were a hazard for the people. Mm. So that's energy resilience, and I measured energy resilience here with the hours of autonomy. How long no, the system will withstand the power outage.
And that will be the
And real tool. Yeah, I can simulate. That is the average hours of autonomy. No, so some days could be higher, some days could be lower, but in a year is, for example, in the case of Puerto Rico, will be 13 hours of autonomy in the average, no, for a whole year.
Thank you. Comments.
So I have a general question about solar.
Yes,
I'm assuming it's rooftop, right?
yes.
So I'm gonna give you now the vision, install the system in my house.
Mhm,
And it covers the roof and it's facing south.
mhm,
And we noticed that the air conditioning need out in Chicago
mhm,
dropped dramatically
mhm,
because of, you talk about coating, but this is basically covering the surface.
mhm.
So I felt like it's offset a lot of the AC need, which in years graph about 20 to 30% of
Yes.
area.
Mhm.
Does your study take into account the shading that these panels do, that actually, it's a double effect, you
Mhm.
generate electricity and offset some of the AC?
Yeah, and Energy Plus, you can simulate that, but I didn't include that in the model. No, what I included, even for colder climates, I put like a light coating in the roof because it will improve the performance of the PV system. Because in colder climates, maybe sometimes the roof is darker, no, to attract more solar radiation. But in this case, for improve the solar performance of the PV system, even in colder climates, the cool roof was included as a strategy. Yeah.
Did you look into green roof cell?
Sorry?
Did you look into green roof cell?
Green roof. No, no, I haven't included that in my analysis.
Hold on, further. I think where you add these dollars is the reservoir.
Mhm, mhm.
Much expensive than the PVC.
Yeah, yeah. So yeah, I didn't look the whole electrical system of the building. In this case, the school building. I included the retrofit, no, changing the light fixtures, no, with LED, no, improving the equipment, so the HVAC system will be improved, no, a new HVAC system, new equipment, for example, computers, something like that, but not the electrical system is not included in the retrofit. And yes, it's a huge part of the cost. Mhm,
The very big problem,
mhm,
because the northern part of the earth,
mhm,
there will be shadows of you. So if it is a fixed to have it.
mhm.
Or maybe a hard box that can be used because this will be the water area.
Yeah, but in most of the cases, it's not the roof area, the maximum roof area, I put like 80%, but actually in most cases is much more less than that. No, so we can, when we install the PV system, we can assess where is the best location because to avoid shades, no, maybe some trees or something like that could be avoided. Yeah.
Okay, thank you all.
Move all the first, Charles.